Hello students, welcome back. Let's resume section 4. We completed up to 4.3. That is, we established factor groups of kernels of homomorphisms. Now let's generalize that for arbitrary normal subgroups. In other words, subgroups with this property. The left coset and right coset are always the same. Now kernels also satisfies the same property, but kernels had something extra. They were directly connected to homomorphisms, but this time we don't have homomorphism to help us out, so we have to do this without help of any homomorphism. That's going to be trickier. How do we do that? Well, let's begin with these. The left coset relation and right coset relation. Remember those? We studied those way back in lesson 6 when we studied coset and Lagrange's theorem, and there we proved that both are equivalent relations. And the equivalence classes were left cosets and right cosets respectively. Remember all those? Now we are dealing with normal subgroups, so the left coset and right coset are always the same, so there's no reason to consider two different relations. Let's completely disregard this and focus upon this one only. And then we're not going to call it left relation anymore because left and right, they're the same. Left coset and right coset are the same, so let's rename those as normal equivalence relation. More precisely speaking, normal equivalence modulo n, because it originated from subgroup n, which is a normal subgroup. Okay, now that we have the equivalence relation, we can consider equivalence classes. Those equivalence classes are cosets, of course, and put everything together, and the set of all equivalence classes is called the quotient set. And then in the quotient set, let's define a group operation like this, induced from that of G. Xn times Yn is Xyn, and this Xy is a group operation in G, so this operation was induced from the group operation of G. But there's a bit of a problem here. This left-hand side expression, Xn and Yn, and also the right-hand side expression, they are not unique. These are cosets, these are equivalence relations, equivalence classes, so we can take different equivalence, different representatives of the same equivalence classes. In other words, we have to consider this kind of situation. X1n may be equal to X2n, and Y1n is equal to Y2n, but X1, Y1, n is not equal to I missed clicking. Is not equal to X2, Y2, n. This is going to be a problem. Same thing in the left-hand side, just written differently, but we ended up with something different in the right-hand side. If this thing happens just once, then everything breaks down. So we have to make sure this never happens. That's what we mean by this expression is well defined. That's what we want to prove. If x1n and x2n are the same, which I just highlighted in blue, and y1n and y12 are the same, which I just highlighted in green, then x1 y1n and x2 y2n are the same. That's what we want to prove. And what property can we use? We can use the property that n is normal. That is, let's see, n is normal. So, okay, all right. Therefore, x1n is equals to n x1 x2n is equals to n x2 y1n is equal to n y1 and finally y2n is equal to n y2. We can switch the order. Left coset and right coset are the same. So we have this property. So we have this blue, green, and purple properties to use to prove this. How do you do that? Well, here's the idea. This is a set inequality, set equality. This set and that set are the same, so we have to prove two set inequalities. x1, y1n is a subset of x2, y2n, and also x2, y2n is a subset of x1, y1n. Or in other words, x1, y1n is a superset of x2, y2n. We have to prove both. We're going to prove only one of them. The other one will be proved in a similar fashion, and I'm going to leave that to you. So how do you prove this? Arbitrary element here belongs to this right-hand side. That's what you have to do. So what do you mean by arbitrary element of x1, y1, n? That means this g is x1 times y1 times some element n of capital N. Then the same g can be written as x2 y2 times some element here, but n is already taken, so something like this. That's basically what we are trying to do. And this one is arbitrary because I'm selecting arbitrary element for here. So this is and in this case, this thing just belong here. So g is x2 times y2 times some element of n. So so there's a subtle difference. This is arbitrary, that's just sum, but in any case, the key part is x1, y1, n form can be rewritten into x2, y2, m form. How do we do that? Well, this entire proof is going to be rather tricky, and following each line is going to be an ordeal. So let me show you all at once, and let's try to analyze it. Here we go. So let's select an arbitrary element from the left-hand side. That means x1, y1 times some n, and that's selected arbitrary, so this n is arbitrary. In any case, n belongs to capital N. Okay, all right, and then we're going to use this blue, green, and purple properties. So, okay, here we go. y1 times n, I can rewrite as y2 times p. What did I just use? I used this green property. y1 times some member of n can be written as y2 times some member of n. So this n, another character p. So each time I select, I have to use different character. They can turn out to be equal to each other by some coincidence, but not always the same. So it's always safer to take different character each time I introduce one. Now y2 times element of n can be rewritten as switching order, some element of n times y2. We switch the order. Which property did you use? This one right here, purple property, but especially the last one. So okay, we are up to here, and then let's apply this x1q and then change the x2r. What property did I use? Blue property. x1 times certain element of n is x2 times certain element of n, but each time I select something I have to use different character because they don't have to be the same. So we are up to here. So we want this x1 y1 changed to x2 y2. We are almost there, but we need some more work. Now I want to move this r over to the other side so that we have x2 times y2 times some element of n. So let's do that. Push over, switch the order. What did I use? I used this property, which I just highlighted in bold. I think I used this one twice when we switch from here to there, and then now from here to there again. And then what do we have here? x2 times y2 times some element of capital N. So that belongs to x2 times y2 times some element of n. Consequence, arbitrary element of this belong to that. So the second set is a superset. The first set is a subset. That completes the proof of this. Now, if you want to prove the other one, use similar technique using different characters and different indices. Same idea, same technique. We are using these blue, green, and purple properties, but all different characters all over again. Good luck. Okay, so we prove that this thing is well defined. So this operation now makes sense. It's well defined. That's the hardest part. Now, whether this is actually a group, that is this associative? Does it have identity? Does it have inverse for each element? Those are much easier. Associativity part, all you have to do is get another coset, xn, yn, zn, and then put appropriate parentheses and use the property in G, and you're going to get what you want. Like this. So this and that are the same. And how about the identity? Well, the operation was induced from that of G, so you have to use E in G. So En, that's a natural choice. So En is the identity, as you see here and also there. How about the inverse? Again, the same idea. Everything was induced from the operation of G, so use X inverse in G. So if you have Xn, the candidate is X inverse n, and indeed, you get the identity to the left or to the right. The second part, step 2, is much easier. Now we have the second method, but we don't have enough time, so if I have time to burn, we are going to come back and do the second proof, the second method. But otherwise, we'll say this is completed. We successfully established a factor group and proved that this group operation is well defined, and then it satisfies all the properties of groups. So we have a group, which we call the factor group.